Yeah, this session is going to be devoted to 4 presentations from the PERFORM program at ARPA-e. The PERFORM program's objective is to introduce the new risks into the analysis of the new risks that were experienced into the analysis of power systems. And without further ado, I'll turn it over to our first speaker, Alex Rudkevich. Alex? Oh yeah, mic him up.
Okay, can you hear me? Okay, now, thank you. So the presentation is called Probabilistic Forecasting of Extreme Market Event. This project is funded by ARPA-e, even though the kind of the twist I'm taking on the developed work is not exactly as we advertised to ARPA-e when we were asking for funding, but that is part. It's actually a little broader than we originally thought. Now let me see if I can. Okay, so extreme market events. This is, we consider it a subcategory of what is known as a high impact, low frequency events. And what is high impact is often in the eye of the stakeholder, right? Depending on who is looking at the event and whether it's a high impact or not. It could be involuntary service interruptions, reserve shortages, violation of supply contracts, or just extreme price excursions. That, from our perspective, that's still going to be an extreme event. Now, when we study the extreme event, and there's a lot of presentations here were on like weather events. Weather is not an output, it's an input, right? We're interested in the outcome resulted from weather and other conditions. And the question is, if we think about it, like what probabilistic modeling tools do we have today to be able to predict such things? I mean, when I say predict, I want to know what is likely to happen, where and when it's likely to happen, what is the probability of this happening, and if should we do something about it, and what can we do something. And if thinking about it, I don't really know what the tools are. We don't have any. The only thing that comes close is the resource adequacy tools. Why? Because they do Monte Carlo modeling. They evaluate probabilities of loss of load events. Now, the challenge, and these I just listed 3 with these tools, is that always rely on very stylized power system models. It's typically pipe and bubble at best. They do not represent physics of the power flow and transmission network. They do not accurately represent operational limitations of unit commitment and the impact of the fact that decisions that are made on the uncertainty. The scheduling decisions made the uncertainty, and then they revealed when the events are happening. So if you take these 3 things and you say, if I'm studying a system under very stressed conditions, would I trust this type? I wouldn't, and nobody should. So what we need for that, we need a high fidelity production costing model at best, right? And run it in a Monte Carlo fashion, because otherwise we will be getting very misleading results. Now that's a challenge. So if we think about sort of probabilistic world of what we want to do, we want to take probabilistic weather scenarios. And when I say probabilistic weather scenarios, I don't mean like P90 or P50. I mean scenarios of comprehensive weather as they happen spatially and temporally, right? Let's say I need 100 of those scenarios. And for each of those scenarios, I want to play out at least 1,000 scenarios of outage of equipment, generation outage, maybe transmission outage. You multiply one by another, you got 100,000 scenarios you want to look at. And if you look at that and say, well, can I actually run 100,000 scenarios of high fidelity model and get a meaningful answer in time, right? So that's really the challenge that you're dealing with. But interestingly enough, the answer is yes, we can. It's just a matter of doing it right. So first of all, if I'm looking at some sort of uncertain event, and pardon my very sort of stylized representation of a certain event by doing the Gaussian curve, right? And if I want to naively spread my analytical efforts, that's what mostly happens in the Monte Carlo models today, then I would waste a lot of resources. Because if I'm interested in the tails, why would I spend my computational efforts in the middle of the range? What I want to do something like that. In the middle of the range, I don't want to spend any of my resources if possible, and dedicate all my efforts to the tails, right? That would allow me to address these events much better and much more efficiently. Question is how to do it. So what we want to do, the kind of our approach to this, and that is ultimately funded by ARPA-e, that we want to run Monte Carlo-based simulation using SCAC and SCAD. We want to run something between 10,000 and 100,000 scenarios. We want to explore them. And the way we do it, we'll say, we set a threshold LMP level in the system, and we'll start screening scenarios with, say, not very high fidelity model, but moderate fidelity model, which runs a lot faster. And start screening internally scenarios and say, well, which are potentially may have a problem, like where the price goes above the set threshold, we'll say, yeah, that's scenarios we need to take a close look at. Then the scenarios that are not potentially extreme, which is going to skip them. And for potentially extreme scenarios, we'll put all the might of the high fidelity model, and then we'll do all the statistical analysis. That's sort of the logic. Now, in reality, since we run the system on the cloud, and we have the automated process of partitioning the models and provisioning machines and running everything in parallel, we deploy two levels of scenario screening. The first one that occurs inside PSO, which is the engine of the system. And this is where the screening of the scenarios based on random outages and based on altering the use of the medium fidelity and high fidelity model. This is where the screening occurs. Another screening occurs outside in, say, we have the partitioning of the problem based on the time dimension and partitioning of the problem based on the weather scenario. So I may have, for example, if I run multiple weeks of analysis, different weeks would run on a different machine, and different weather scenarios also would run on a different machine. So that kind of the level of partitioning that occurs. Now, when we study, again, it depends on what we're looking at. Inside the model, because remember, we're talking about also the making decisions using, relying on uncertainty conditions. So there is a whole logic of the decision cycle. Depending on the decision cycle selection, the type of event that we are looking at may be varied by the user, but the logic is still the same. It could be day ahead scenario, it could be intraday scenario, it could be even real-time scenario. And effectively, what we're doing, we're taking the traditional production costing model and we turn it into effectively resource adequacy model. We run the Monte Carlo simulations and we do it in two rounds, as I described before. One with the sort of simplified optimization formulation, which gives us the reduced fidelity. And then for the prospective scenarios we apply the high fidelity model. The second thing is what happens is the filtering of the scenarios. So we evaluate all weather scenarios first at the first stage, and we identify which of the weather scenarios are actually worth of proceeding to. So if I look at 100 weather scenarios, out of those maybe a handful actually of interest. The vast majority turn out to be not a problem, and we shouldn't spend computational resource on that. So the whole process is designed to automate that and then perform an allocation of computational resources to the interesting scenarios. Well, we don't decide which is interesting ahead of time. We let the models, the software, to make the selection. If we're dealing with the multiple weeks and the multiple weather scenarios, the same logic. We created initially a lot of segments, dedicated machines to explore every segment, and then identify which segment should be exposed to the whole might of the computational power we get on AWS. How we allocate the machines to the scenarios. That's the thing. In general, it's the same stratified sampling that pollsters are using in their practice. So I'll give you a couple of results, example results of applying this thing. One is the nodal study of resource adequacy of airport for 2024. We just took our commercial model that we use and say, let's run it in a Monte Carlo fashion and study the resource adequacy as we would like to do it, nodally, with all transmission constraints, with unit commit and everything. So just give you a summary. 1 year, one weather scenario in this case. We partition it and we got the results of everything that we wanted to. It was 10,000 scenarios run in 2.3 hours turnaround time. The overall usage of the compute hours on the cloud was only 113 hours because a lot of weeks which we looked at were very quickly dismissed as not interesting. And the whole cost of this exercise was, if we were using spot instances on AWS, is $13 or in AWS charges. If we use the on-demand instance, $57. It's pretty, I would say, efficient. The results that we're getting are quite interesting because we can see under what conditions, on which days, because every detail of the shortage scenarios is meticulously reported. Which transmission constraints were binding, which generators were on outage, what the pricing were occurring. So all of that is there. And we can identify and analyze what happens on August 6th, where we see this at 6 p.m. What happens at 6 p.m. on August 9th, where we see something else. So all these details are available. The other example is actually what was funded by ARPA-e, was to do the, to analyze the next day ahead for MISA. And again, this is one example. We simulated 1 day back in 2021, June 10th, using the MISA commercial, our commercial model for MISA. The only exception where it was not our data, the MISA provided historical load for that day with the high fidelity that we didn't have access to. And then we ran, SCAC and SCED high fidelity model. That was run for a day. We had 100 weather scenarios provided by IBM Weather Company. They had weather forecast for every location in MISA. Every wind farm got its own forecast. Every solar farm got its forecast. So again, we used 500 virtual machines. Each machine ran 200 random draws for the day, full unit commitment with, pre-screening, of course. So all was done in 45 minutes. No, it's not a year, it's a day. but it's done in 45 minutes. It's a big system. It took about 300 hours of virtual machine time. And the cost, if we pay on demand prices, would be $200, and in spot instances, which may delay the getting the results, is actually $120. The kind of results we get, again, is highly detailed. For every outage event, every shortage event, we see where it happens, what happens in the neighbors, how every generator performs, which transmission constraints bind. I'm not going through all the details that are available, but we are currently in the process of developing a variety of visualization tools for that. And again, we see where constraints are limiting the performance of generators, how it's all allocated across different locations in MISA. So in sum, what we found that we were not actually intended initially when we got the funding from ARPA-e to solve the annual longer term resource adequacy problem. We thought that we'll just focus on what I was describing for MISA, just one day, maybe several days ahead. Well, we realized that the method that we actually applied turns out to be extremely scalable because it very quickly goes through a lot of cases and dismisses them. Right, and that allows us effectively to say we can look at a lot of weather scenarios at a lot of weeks and get reasonable results in a very reasonable time and cost. So, and it could be applied not just for resource adequacy as we think, but a lot of other potential applications. And so, thanks.
Yeah.
Wow.
Okay, our next speaker is Dan Bienstock from Columbia University, and he'll be talking essentially on the same subject. Oh, mic yourself up.
That's just okay. Well, good morning. I'd like to thank Dick for having us here, and I would like to thank ARPA-e for funding our program. We have a number of different backgrounds represented here: power engineering, optimization, financial engineering, and machine learning. And I'd like to give you a quick outline of our program and what we are doing now. So I would like to open up with some remarks that I heard a couple of weeks ago at PSARC. PSARC is the Power Systems Engineering Research Consortium that it's made up by industry and academic representatives. And one of the ISO representatives made those statements, that at the start of a 5-minute time window, renewables can still present a lot of uncertainty, or volatility would be the right term. You cannot make up 100 megawatts just like that. This was a verbatim one of those statements, and he was referring to renewables. The goal of our program is to provide tools that can help market participants make better risk-aware decisions. Any market participant. At the top level, we have tools that run outside of the SCUC, but that help participants adjust their positions relative to the market in order to make them better risk aware. And we also have updated versions of SCUC itself, which of course are not likely to become deployed anytime soon. This is all put together into a software product that we are calling the Risk Dashboard. I actually have background selling software for risk management to the financial services industry. And some of the outlook in this program is informed by that. We're working with New York ISO and ISO New England and we are looking for additional partners. Here's a very high-level outline of the functionality that we provide. I would look at toward the right of this panel. We provide analytics for looking at the trade-off between risk and cost and how to make additional decisions. We also provide the design of a number of what might be termed financial instruments that can be deployed by participants to defray their risk in or outside the market. And of course, analytics, together with a lot of visualization of the results. And I will discuss some of the boxes that you see here in extra detail when we get there. Here is an outlook that comes straight from the financial services industry. And in particular, I would like to point out the first bullet point. The Basel Committee was established almost 20 years ago, after a number of banking crises and so on. And it's a very entertaining document to read. But in particular, it highlighted the importance of deploying the correct scenarios for analyzing risk. And the sentence that you see there is one that's taken directly from that report. You know, you want to have scenarios that are severe because you're engaged in some form of stress testing. But the scenarios should be plausible, not crazy severe. And moreover, the scenarios should be informative. They should help you make better decisions. Okay. Currently, the energy markets are not informed by any such scenarios. There are no scenarios for risk in terms of deviations and renewables or load, or, you know, it's N-1, it's security constrained, but that's about all that it is. Now, one could argue that modeling using dynamic reserves could incorporate in a way such considerations. It could, but it's not done. So our methodologies do not require any change to the current setup for SCUC or RUC or real-time dispatch. But what we aim to do is to provide a rapid and online evaluation of the outcomes of the markets so as to provide a map of the risk, live, as it were, not offline. And of course, we are developing our own versions of SCUC and so on. One of the main techniques that we are using, which is a known technique, again, in the financial services industry, is that we're, here in energy, we are looking at risk that is high dimensional or multi-dimensional. For example, risk arising from shortfall in output from a collection of wind farms. So it's a number of wind farms. They're going to be correlated. The correlation structure is non-trivial. It has to be taken into account. It has to be a data-driven setup. Principal component analysis of weather, of wind, whatever you name it, is going to reveal the typical structure, which is that even though it is high-dimensional data or multi-dimensional data, in effect, there's a very low-rank substructure that should be exploited. And factor stressing does exactly that. Okay, it's not a technique that we invented for this program. It is something that is used in the financial services industry. You identify the latent factors, and then you create scenarios by stressing along those factors, thereby creating data realizations that are aligned with the data that you see in terms of the correlation structure, but is pushing along those directions. Here's the dashboard in a little bit more, or part of the dashboard, a little bit more detail. So let's say that we have the SCUC solver running. SCUC solvers are running linear mixed integer optimization, depending on which ISO you are looking at is going to be slightly different. No two of them run the same SCUC. That's another, well, that's something I think we all know, but that was another statement that was made by an ISO person at PSERC, that no two of the SCUCs are the same. So it's not SCUC, it's somebody's SCUC. So it's running a solver. The solver will be producing solutions or incumbents, as the solver calls them. And it takes a while, it takes hours probably until the termination. As the solver is computing new solutions, there's no reason that that should be all. Those solutions can be examined live. The solver keeps running, but once you have a solution on hand, you can run analytics on that solution and display them visually, run a financial analysis, display it graphically. This way the operator is seeing what's happening. And as better solutions are being found, more and more information is being deployed. So this is something that I saw in a similar process in the financial services industry. Again, something was being solved, solutions were being computed. Eventually, this algorithm would converge to some kind of an optimal solution, but there was no need to run the solver to a mathematical optimality. Structure was being revealed. The persons running the software would learn about their own system by seeing the analytics deployed graphically about the different solutions. And a button was being provided so that the optimization could be stopped as soon as the solution displayed characteristics that were nice. I'm referring to the linear mixed integer optimization. And the SCUC operation after that is done, the binary variables, which are usually generator commitment decisions, they are fixed. And then you run now a linear program from which the dual variables are extracted, and these are going to be the day-ahead prices. So that second part is we are not going to alter at all. Functionality is the same. But we believe in this thing of having that button that where now the ISO person sitting at one of those desks can see the analytics being visualized and understand what's going on, and then can stop the optimization when they see something that they like very much. And in any case, they will learn by seeing the displays. The adversarial component is going to be an important element there, as well as the recommendations. Okay. And this is the same thing in a little bit more detail. And the box on the lower right is what I was referring to. Now, the second item in the box, that refers to the updated version of SCUC, which is something that would not be used today in the markets, which is that it is a SCUC that is risk aware, financial risk aware, for example. And the quantity being optimized in the computation incorporates a measure of risk. For those of you who are familiar with this theory of portfolio optimization, you have a portfolio optimization. It's an optimization problem, and you're maximizing return or reward, but there's a penalty for volatility. So imagine updating the SCUC so as to include a term like that. And as candidates are being found, that the optimization is updated to take those into account. Okay. One example of what we call stressing, we have applied. So in our program, we are working with New York ISO. I should add that. The biggest thing happening to New York ISO today is that they're going to add a lot of wind in an unfamiliar place, something like 5 gigawatts coming online in the next few years, and it's been signed into law. And this is a huge deal for them, and they are aware of it because they're going to have power coming from the east on newly constructed lines. I think they remain to be constructed, plus new substations in a very challenging environment. If any of you are familiar with Long Island, you're probably going to wonder, well, where are they going to place those lines? Moreover, it's expected to happen because in tandem with doing this, they're going to be shutting down thermal units upstate, that on various days during the year, you'll have power that is flowing from the east toward the city, and not all of it is consumed in the city. It continues north and thereby totally reversing the power flow setup that they have today, where they have a lot of power coming north to south and congesting lines that are coming from the north to the south. So they're very concerned about the risk. They're concerned about the risk of brownouts in New York City, which would be quite the event. And of course, there's a huge financial risk element. They really are very concerned. They're really taking this problem very seriously. It's something that we like very much, of course. And it's something also that is new. We've been working with Perform for 3 years. Until I would say a year ago, such concerns were not were not seen by us. Okay, something has changed within the last year, and it's a good thing that it changed. And we're using this stressing system. So here's one example. We have developed a careful methodology for forecasting wind power at these locations where I think it's 6 wind farms that are offshore, something like that, will be placed. And there are 26 different components in the model for which we have data, and they are put together to provide a forecast for wind power. So it's a 26 by 26 correlation or covariance matrix. However, when you plot the eigenvalues, you see the usual real-life pattern for a covariance matrix, which is that the modes decline very rapidly, very, very rapidly. After the third one, it's a noise. And so you construct a low-rank model using the 3 modes there, which are vectors in the PCA setup. It's all data-driven. There's no interpretation as to what these factors are. They're just vectors, 26-dimensional vectors. But you stress along those to create genuine scenarios. The other way we are creating scenarios is by using AI, generative networks. Now what we like about this version is that whereas in the prior version, it was effectively a statistical methodology. We generate scenarios that are statistically valid. Here we are learning where the eventual target is cost, system cost, or cost of load of lost load. And we create scenarios that stress in that direction. The generative adaptive network technology in AI was created for generic purposes. That you have a trained network, and now you're going to generate data instances that challenge the trained network, that make it behave improperly. And those data instances are gold, right? Because that's where the network fails in its prediction. And in the GANs setup, once you develop such challenging data realizations, so again, the data realizations in GANs are as follows. You take a realization that is handled well by the network, it makes a good prediction, and then you perturb it minimally so that the trained network totally fails. And then you take that data instance and you add it to your training set to retrain the network, and that makes it far more robust. And so that's exactly what we aim to do here with system cost or cost of lost load as the target. Here we have some pretty pictures. Oh, sorry. Okay. Speaking about pictures, this is part of the visualization effort in our dashboard. Display the usual things: congestion, load shedding, spillage, LMPs, and so on, but also the financial statistics and the risk. And as I mentioned before, this should be done interactively with the solution procedure, the SCUC solution procedure. The learning, now I'm referring to learning in the human mode. Somebody is running this. The learning that they will experience by visualizing the attributes of the solutions is something that should not be ignored. And so here we have some more pretty pictures. This is code, okay? These are not pictures that were generated in order to have slides. This is our code running, generating these pictures live. And as I said, this is all New York ISO. The data team, one of the data teams from Wisconsin created this realistic but ultimately fake New York ISO system, which we supplemented by doing a lot of data fishing on our own from publicly available sources, including scraping data from websites and so on. So once a solution has been computed, we want to do the financial analytics. That involves running a fast simulation of real-time outcomes. And the setup that we have, for those of you who are computational jockeys, is a usual master worker setup. You have N workers running in parallel, and they have M jobs to run. There's a master procedure that is dishing out the work to the workers in order to maintain even loads among the workers. And then every time that a worker is done, or every so many simulations, the visualization is updated. I could have run live this setup, but we are not permitted through this. But if anybody wants to see it, I can run it. I have it on my laptop. For this New York ISO system with 1814 buses on a, let's say on a 10-core laptop, we can do about 1,000 real-time runs per second. And we think we can do substantially more than that, but 1,000 per second is already not too shabby, I think. Now financial tech. So this is a big part of our program. You probably are aware that Corey Hedman played a substantial role in creating the PERFORM program, and he was very keen on having the financial perspective. And so we want to design financial instruments that can be deployed by market participants, any market participants, to reduce their cost. And it's a pure financial play. There's the day-ahead market, and then there's the real-time market. There could be a disparity, and thereby there's risk. If you're concerned about the risk, you can choose to spend some money and buy some instrument to help you defray the risk. You'll have to pay for that instrument, but you may deem it worthwhile because it will protect you from some much more severe outcome. And it's a form of insurance effectively, but the critical part is how do you set up this instrument? And most important, how do you price it? So the pricing of financial instruments is one of the main pieces of work in the financial services industry. How do you price it properly? Okay, and so here we have some examples of potential participants that could invest in the loads. Of course, the LSCs would be, we think, could be those who would be buying such instruments. Anytime that you have a financial instrument, there are two parties. There's a party that issues it, and there's a party that buys it. And then the cash flows are the negatives of one another. So at any given realization, one will make money and one will lose money. However, that's the same that it is in the financial services industry, and yet these things are sold and traded. One way to think about it is that the two different parties are looking at their cash flows from a different perspective. They're exposed to different types of risk. One is being protected against one extreme form of risk, and the other one doesn't care. So their risk perspectives are different. The time frames by which they want to account their cash flows could be very different. So there's no contradiction in there. The fact that there are two parties and in this transaction, one makes money and the other one loses money. They may both gain. They probably do. And so here's an example. I know that there's a lot of data. BAU is business as usual, and RD is the dispatch that is risk aware. You can see here that the RD columns are always higher than the business as usual columns. It costs more to be protected against risk. Okay, of course it costs more. However, on the road that has the lost load, EENS, you can see that the risk-aware dispatch experiences a lot lower lost load. And so the instrument is doing its job. You can think of the one counterparty here as being an LSC that's buying the instrument. The other counterparty would be somebody, for example, that is an energy provider, like a battery operator, who stays away from the energy markets for the purpose of providing the service. And they're being remunerated by participating, by selling this financial instrument. They're being paid more than they might get paid if they were to participate in the energy market. So they stay off of the energy markets. SCUC is totally unaware of this. However, the LSC is investing in this instrument to protect itself. Okay. And the ENS row is what we are interested in. Now here, this deserves some explanation, okay? In this case, what the pictures aim to show is that when the instruments are being deployed, there's more wind farm output. So the wind farms in New York State today, this is prior to the deployment of the offshore units, are upstate. So the orange balls on the upper right in particular is where they have some of their bigger wind farms. And so in this simulation, the deployment of the financial instruments leads to greater real-time dispatch of the wind farms. And however, the gas units are used to back up, effectively to back up the wind farms. And I apologize for this typo that I'm noticing now, the biofuels. And with that, I will conclude my presentation. I don't know if I ran over a little bit. Okay, thanks, sorry. I can answer any question or offline. And as I said, we are interested in talking to more industry, and we are talking to a lot of other industry right now.
I'm sure our discussion will be robust after the presentations. The next presentation will be by Dimitris Floros, Duke University.
Can you hear me? Great. Good morning and thank you. It's a pleasure to be here today and to share with you our progress on the GRACE project. We have received funding from the ARPA-e PERFORM, and as we speak, we're at the beginning of year 3 with promising developments on the horizon. So we seek to contribute to 3 major challenges, which I will explain here. The most critical function of electric power system operators is to keep electricity generation and electricity consumption or load in balance at all times. And this delicate balancing requires careful planning. So ahead of time, system operators must consider the forecast of electricity demand and the forecast of electricity generation from wind and solar resources, and the availability of the conventional resources to schedule the operation of conventional generators. And this schedule is such that it minimizes the expected value of the total costs of operating the system. Now, this process of balancing the forecast of load with the estimates of the renewable production and the conventional resources schedules is the unit commitment process. This process specifies the schedules of the conventional resources and how much of their capacity will be kept as reserves. And these reserves are a guarantee that generators have enough headroom and floor room to adjust their electric power output as needed, so that power system operators can react in real time to any errors in the forecasts of the load, the wind, the solar, or to unforeseen outages of the generators or the transmission lines. Now, system operators schedule these reserves to meet a target that they consider adequate in order to minimize the risk of expensive adjustments or outages or blackouts. And setting this target is a great challenge, exacerbated even more by the renewables. And this is where GRACE strives to make a significant contribution. Now, in real time, conventional generation may fail and may become unavailable, or its potential to generate the electricity may be derated. When this happens, power system operators must adjust the plan that they had for conventional generators and other controllable resources. And the operators must make this adjustment taking into consideration the schedule of the power production and the reserves. So when the output from the conventional generators is added to the actual electricity production from the variable renewables, there is a perfect balance. And the second challenge is how to use detailed and current information on the intrinsic risk of the conventional and the renewable assets, but also a characterization of the weather-based risk. And the third challenge is how to penalize and reward assets according to their effects on the system risk. So the objective of the GRACE project is to develop a novel framework that considers the risk in power systems imposed by weather-based and intrinsic uncertainty. And we investigate approaches that are computationally tractable and are scalable to large power systems. Ultimately, GRACE will minimize the operation costs, maintain or improve system reliability, maintain or improve utilization of low carbon resources, and quantify the impacts of grid resources on system risk. I will briefly introduce the GRACE team. GRACE is a collaboration between 4 universities and the Pacific Northwest National Laboratory, Professor James Smith at Dartmouth, the team at Duke University led by Professor Dalia Patino-Echeverri, the team at North Carolina State University led by Professor Jordan Ken, the team at Ohio State University led by Professor Antonio Conejo, and the team at PNNL led by Veronica De Tolla. Our industry partner in the project is Duke Energy, with a total capacity as of 2020 of 62.6 gigawatts, out of which solar is about 10% at about 6 gigawatts capacity, which is roughly 6.6% of the total US solar capacity. DC and DP, the Duke Energy Carolinas and Progress, became the largest vertically integrated utility in the US in 2021 after the merger of Duke and Progress Energy. The total generation in 2020 was 171 terawatt hours, out of which 3.5% was solar, or 6 terawatt hours, and this is about 7% of the total US solar generation. And I also want to emphasize that Duke Energy has a 2 gigawatt of pumped hydro storage capacity. Now I will discuss the overview of our proposed energy management system. It is composed of 5 pieces. The first piece is a model that characterizes the uncertainty affecting system operations, be it intrinsic or weather-based uncertainties. The second piece is a risk-adjusted unit commitment model. This is a risk-averse stochastic optimization model that finds risk-aware reserve requirements. Risk-aware reserve requirements are the levels of reserves required to minimize the risk-adjusted expected cost of satisfying electricity demand. And the risk-adjusted expected cost is the expected value of the cost plus the expected risk. The third component of GRACE are the libraries of risk-aware reserves. They are found by pre-processing the data some time ahead, and these libraries contain a large set of scenarios of archetypical system conditions regarding renewable energy, load, the infrastructure performance, and the corresponding optimal solutions for the commitment in these cases. The fourth component is a library search engine that allows retrieving information from the libraries without running the stochastic model or running a simplified version of it that runs much faster than the original one. And the last component is an algorithm that uses the library search results to compute the commitment and the risk requirements to have a schedule, a day schedule that is risk aware and yet easy to implement in today's utilities. So the first component of GRACE is a model that characterizes the different sources of uncertainty. And we focus here on weather-based uncertainty in this presentation. First, we analyzed the residual errors of the single point or the deterministic forecast that Duke Energy used in 2019. And we saw in this plot the distribution of the error across all days of 2019 in megawatt. So we are looking at 7-day ahead or week ahead forecasts, and we see how the errors increase as we look further into the horizon for the demand in the Carolinas region. We also saw the forecast for the PV generation in the Carolinas regions for the 7-day ahead forecast period. Now, having analyzed the errors in the deterministic forecast of Duke Energy, we turn to probabilistic forecasts. And we need 3 components in order to investigate the grace benefits. The first one is the actual time series or the observed data, which is what we will be using in our real-time simulation. The second one is a single point or a deterministic forecast to use with the current practice model of Duke Energy. And the third one is the probabilistic forecast to use with the grace approach. We enforce that the expected value of the probabilistic forecast is equal to the deterministic forecast when we make the comparison. And this helps us make and understand the comparisons between the 2 models, the current practice model and the grace model. And the actual can be, the observed value can be any historical year or any synthetic year, a plausible synthetic year. So we show an example of an actual that was observed in 2019, a single point forecast from Duke Energy in red, and in gray, the probabilistic forecast that Grace will use within the stochastic model. Now, we use the error structure from the Duke Energy forecast in order to generate the different probabilistic forecasts. And we have developed several methodologies for this, and historical sampling, Monte Carlo approaches, and some baselines for us to test against. Now, the question for all of this is in the quality of the forecast and how do they compare with each other. Specifically, are the scenarios realistic? Are they plausible? And how do the different approaches compare in realism and in the forecast accuracy? So we demonstrate what we mean by realism. We saw an observation from 2019 in blue and 3 different scenarios from a Monte Carlo approach in a probabilistic forecast. Now, first we look at the profiles of the scenarios and would quantitatively compare the scenarios in terms of the distribution of the values, the autocorrelation function, and the step changes. That is the changes in the value of each variable from 1 hour to the next. And the step changes are particularly important because extreme, non-plausible step changes in the scenarios may lead to infeasibilities in the unit commitment model. Now, having forecast ensembles or probabilistic forecasts of loaded solar generation, we turn to the second component of Grace, which is the risk-adjusted unit commitment. The risk-adjusted unit commitment is a stochastic optimization model that takes as input the probabilistic forecasts and minimizes a function of expected cost and risk. And it considers the different scenarios of possible futures, and we minimize a convex combination of the expected cost and the CVAR. It is a 2-stage optimization model. In the first stage, we do not consider the load. And in the second stage, we consider the startup of the fast start generators, as well as the production costs, the load setting, etc. In the first stage, we have all of the operational constraints on the units and the time periods. And in the second stage, it's across the different scenarios, and we're trying to match each scenario with a particular probability to meet the demand under each of those scenarios. And our formulation follows the optimization of conditional value at risk from Rockefeller and Urisev 2001. Now we compare the current practice energy management system that Duke Energy uses with the Grace energy management system. So in the current practice, Duke Energy schedules the operation using 2 optimization models. The first one is a unit commitment model that looks 1 week ahead, considers the initial condition of the power plants, whether they are on or off, how much they are producing, and how much they can produce, and one single forecast, a deterministic forecast of demand and PV production. They run the models at least 2 times a day. The first is the first unit commitment model, the FUC, at 6 a.m. And then the output of the model is the optimized commitment for the whole week. And optimized commitments is the production schedule for each power plant in the system. Now, every hour, they have to adjust the schedule to balance the supply of conventional units with the actual value of demand and supply production. And they run again the week ahead unit commitment at 5 p.m. That's the second unit commitment. Again, the problem here is that we are only using a single point forecast, a deterministic forecast. The risk-adjusted EMS of Grace is the same process, but now it uses a risk-adjusted unit commitment that considers the uncertainty in the future. And we saw some preliminary results of a simulation with the 2019 fleet of Duke Energy across 250 synthetic years. And on average, the system costs are 2% lower than the current practice, and the tails in the distributions are weaker with the risk-adjusted approach that is in red. The cost reductions overall vary in the 250 synthetic simulations from 0% to 5%. And we also show the difference in the operations between the two models. Grace, in red line, uses steam turbines more and less of natural gas combustion turbines compared to the Duke Energy, which is in blue. And this drives the cost reductions. Also, Grace uses storage more intensely, the pumped hydro storage that I mentioned earlier. And in this example, the risk-adjusted DMS reduces the monthly fixed cost by about 5.3% and the fuel cost by 1.3% for a total of 2% reduction. And we now move to the third component of our EMS, which is the solution libraries that we have generated from the risk-adjusted unit commitment model. Now, what is each book in the library is a pair of probabilistic forecasts and the risk-adjusted unit commitment solutions. And the library is a collection of these books for the same common initial conditions, for example, for the availability, the durating, or the fuel prices. Then whenever we have to solve the risk-adjusted unit commitment for a new day, we look into these libraries to find a book that is the closest one to that new day and use that solution if we can for the optimization. And we need several libraries so that we can capture the different initial conditions that may occur in the future. Now, we may use these libraries in different ways. For instance, we can use them as the initial solution to the risk-adjusted unit commitment to speed up the optimization process. Or we can use them to enforce some scenarios in the first stage, to fix some binaries and to relax some constraints in the optimization problem, or to completely avoid running the unit commitment and extract the reserve targets directly from the libraries, and then use the current practice commitment with the new reserve targets. And we will discuss a bit the third option in the next slide. A challenge with a stochastic unit commitment is that it is computationally expensive. And the number of binary variables increase with more scenarios, making the mixed integer linear program harder to solve. What we have observed is that some binary variables in most cases are always 1 or 0, depending on the initial conditions and the forecast. And we could fix these commitment variables and remove them from the optimization model. And we can also identify in the same way non-binding constraints and also relax them and remove them from the optimization problem. Now, the question here is how we can accurately identify these variables and constraints and when we're trying to solve a new unit commitment problem. And this leads us to the fifth step of the GRACE approach, which is how to determine the daily schedules for the utility using the information that we have from previous optimization problems. And a potential approach here is to check whether we have seen the same exact conditions before, and if so, we just use the solution for that day. But this is not very likely to happen, and we will not be able to use the solution of the previous day unless if the initial conditions are different. So we need to define some similarity function, and depending on whether 2 days are similar or not in terms of the commitment, the cost, the forecasts, we use the solution of the previous day as in the new day. Otherwise, we solve the risk-adjusted unit commitment either from scratch or by eliminating binary variables or constraints, as we showed in the previous slide. At the end, we propose that we can run the current practice model in parallel to the risk-adjusted model and use the current practice solution if the risk adjustment hasn't finished in time. And the advantage is that even if it did not finish in time and we couldn't use the commitment, we can still use the solution in the libraries. So whenever we have a new day that is similar to that one, we will be ready to use it and solve it. So in conclusion, Gray's approach is promising by our initial experiments, and the risk-adjusted unit commitment does reduce the expected value of cost and increases reserves availability. We're currently running simulations with the 2030 fleet of Duke Energy, where we expect even better results with higher penetration of renewables and storage. Also, the library system is promising in improving the efficiency of the unit commitment, but there is more work needed to be done here on the different uses of the solution libraries. And I would like to mention that we do seek collaborators that have access to weather measurements along with forecasts across different regions or granularities, and the operation schedule of power plants in order to test our approach on different systems. Thank you very much.
Our next speaker will be Michael Blonsky from NREL.
Okay, thanks. Thanks everyone. Thanks Dick and ARPA-e for and ESIG for having us here. A lot of similarities to some of the other presenters from this session. We're going to focus a little bit more on the ISO markets, proposing a new market product, and also thinking about how some other types of market participants, DER aggregators, can participate in those markets. So I don't need to go into an overview of the PERFORM program. I'll just say I'm presenting on the work that NREL was leading. We were working with Johns Hopkins University, EPRI, and Kilowatt Hour Analytics, a small insurance company that provides products for solar products or solar plants. And our project was really focused on two different things. One was looking at flexibility from different types of resources, in particular DERs, as well as physical and financial products to hedge risk. So I'll start with that and a little bit of background. We've talked about many types of risk, including net load and balance risk, really for the whole past 2 days and the past few sessions. I think I'll skip this for the most part, but just say that imbalance risk is a big issue. Many ISOs are seeing it. We're looking at gigawatt scale net load imbalances between the day ahead schedule and real-time actuals or the real-time schedule. 3 gigawatts here in MISO for a single day, and many days throughout the year in CAISO above 4 gigawatts. So, okay. The main takeaway here, our sort of philosophy for this project was we have this energy market, day-ahead energy market that balances supply and demand, and we have this big source of uncertainty from net load imbalance, and we think maybe we can use the same concepts from the energy market to balance uncertainty with a different type of resource, which is flexibility. So we have energy providers and energy consumers in the energy market. Maybe we can think about a flexibility market in the same way, where we have resources that generate uncertainty based on uncertainty in their forecasts, and we can balance those out with flexible resources that can manage that uncertainty in real time. And so using that philosophy, we created this market product and concept that we're calling flexibility options. One of the collaborators on this project, Professor Gieman from Johns Hopkins, she's a professor in finance. She likes to talk about flexibility in parallel with optionality in finance markets. Financial options give you the chance to, or the right to purchase or sell a commodity or a stock. in the future. And there's a lot of similarities between that and flexibility, where you can produce or consume energy at some point in the future based on a strike price. So at a high level, the product that we designed, called flexibility options, they use probabilistic forecasts to determine the amount of uncertainty in the system and therefore the flexibility requirements for a particular hour. On the supply side, sellers of these flexibility options would provide flexibility bids using strike prices, which would determine the cost and the value of flexibility. And an important thing to note here, there's a lot of flexibility and reserve products out there already. This would be co-optimized with the day-ahead market, and so it would impact the unit commitment problem. A little bit more detail on how it works on this slide. So before the day-ahead market, there's day-ahead bidding for both the buyers and sellers. The buyers would be expected to submit a probabilistic forecast to the ISO. The ISO can specify specific tiers that they're looking for to specify at which levels of uncertainty they need to quantify. And then on the seller side, they would submit something that looks very similar to a demand curve or a supply curve. But in this case, it would be for flexibility rather than energy and specifying the strike price. So this information would go to the ISO. They'd use it to co-optimize the day-ahead market, energy and flexibility products. You'd get the same products or the same outputs out of that, that day-ahead market, in addition to a few extra ones from the flexibility market. So you would get the number of options, the option quantity, the option premium, and again, for each of these different tiers, so you can specify what's the value, what's the amount of flexibility we need at different percentiles, and then finally the strike or the value of flexibility at those percentiles. In real time, we would determine whether this flexibility is actually necessary to activate. So we use a double trigger activation. The main trigger is based on the real-time price. So if your real-time price exceeds the strike up price, you would activate flexibility up or increase generation, opposite for flex down and the strike down price. But we recognize that you can't just base it on the real-time price. If the net load imbalance isn't in the same direction, then your flexibility would actually be counterproductive. And so we have this double trigger. You need the price high as well as the real-time, the net load imbalance high. A significant proportion of the time, these are correlated, but we want to make sure that they're not causing any problems with the system. And then another important thing to note, these options are purely a financial product. So the financial settlement happens after the real-time activation. It's based on the option premium. So the buyer would pay the option premium. The seller would receive that same premium. And then if the activation occurs, a certain amount would be paid by the seller back to the buyer, depending on that strike price and whatever the real-time price was, so the difference between the prices. Important to note, it's revenue neutral for the ISO, and it does lower the revenue volatility both for buyers and sellers, because neither of them have to worry as much about fluctuations in the real-time price. So to dig into that a little bit more, benefits to the sellers, if you're a gas plant, a battery, a DER aggregator, you can schedule your flexible resources in the day-ahead market, have a little bit more certainty on when they will be scheduled and when they're likely to be used. And you get this consistent revenue stream from the option premium. Don't have to worry too much about real-time energy arbitrage or something like that. Benefits to the buyers. So if you're a solar plant or a wind farm or a load serving entity, and you're worried about not producing as much at certain times when it's not as windy or not as cloudy, and worrying about having to purchase energy in the real time when prices are likely high, you don't have to worry about that as much. You have to pay this risk premium, pay the option in advance, but you don't worry as much about the price spikes. And then benefits to the system, the ISO is able to incorporate all of this into the unit commitment problem, able to manage how much flexibility is necessary based on uncertainty. We can reduce total system costs. and create a market-based value of flexibility. I'm a little nervous about presenting this slide to this audience, but I'm going to do it anyway. There's a lot of work being done by these check marks. I recognize that, but I wanted to give a product comparison on what's out there now, what's been proposed, and these flexibility option product. So there's virtual bidding, which is already used widely and used to hedge real-time prices against day-ahead energy prices. The flexibility option could do something similar, but instead of hedging with day-ahead prices, energy prices, it would be these flexibility prices. And then multiple flexible ramping products, the imbalance reserves, reserves in general. I think there's a lot of overlap between these products. The imbalance reserves in particular are probably the most similar. It's one of the few products out there that considers uncertainty and operates in the day-ahead market. One of I would say the main difference between our product and the imbalance reserves in CAISO is that because the units with uncertainty are presenting that uncertainty to the ISO, they are the ones that are going to be paying for this option premium, and therefore they are the ones that are going to be most burdened. Essentially, the more uncertainty you have, the more of the burden is on you to pay for this extra need for flexibility, and so that incorporates cost causation that's slightly different in the imbalance reserve case. So a little bit on our simulation results on the market design piece. So we use synthetic data, system based on the ERCOT system. This was all from the data partners from PERFORM. Texas A&M created the system. We used probabilistic forecasts and actual data from Princeton and NREL to run these simulations. We ran 3 different cases. One is uncertainty ignorant, so not incorporating uncertainty in the day-ahead commitment, essentially not having enough reserves. So a lot of the extra cost in that system is due to a loss of load. And then an imbalance reserve case and a flexibility option case. The main differences between those two and the uncertainty ignorant is that the number of units that were committed day ahead was increased. So more reserves, more likely to suppress real-time prices, lose not as much loss of load. And a small difference between the imbalance reserve case and the flexibility option case really has to do with redispatch costs. It created a slight cost savings between the flexibility option case and the imbalance reserve case. So I'm going to shift a little bit now to the DER market participation and how DER aggregators could participate in this flexibility option market in addition to other flexibility products or just really wholesale products in general. I'm going to stay away from the FERC 2222 issues. There's a lot of things that people have talked about in the past few days. Issues on the distribution side, on the size of the aggregation. We really focused in this project on how can a DER aggregator optimally bid into a set of products or a set of markets based on the information it has on its fleet. And when I say DERs, a lot of people mean different things. I mostly focused on flexible loads, so not resources that can be flexed, so not PV, rooftop PV necessarily, but also not necessarily batteries. Batteries have some of the issues of DER, of flexible loads, but one of the key issues that we wanted to look at in this project was flexible loads because they have flexibility, but they also have uncertainty related to occupant behavior and weather. So that's one reason why DERs and DER aggregations are a little bit more complex than other resources. The aggregator has to determine how much flexibility there is, but also consider the fact that uncertainty is dependent on weather and occupants, and therefore probably needs to reduce the amount of flexibility that they can bid in order to be certain that they can provide what they're saying they will. Another challenge is that these resources are distributed. There's many of them. They're not always the same. Take an EV from someone who commutes and has a pretty consistent charging schedule versus someone who doesn't and charges at random times of day. They can have different amounts of flexibility based on time of day, different uncertainty and when they're going to be used, and therefore how much flexibility they can have. And so an aggregator might be interested in partitioning their fleet into assets that may be more flexible or more reliable at certain parts of day, or just a more reliable set and a less reliable set. So really the main question for the DER aggregator is how much flexibility can we offer in these markets? And I suppose which markets should we participate in? So we were primarily looking at participating in the flexibility option market, in the real-time market, and then considering any sort of delivery penalty costs. And so the optimization was to maximize the market revenue of the DER aggregator. We used a two-stage stochastic optimization problem, not too different from some of the other things talked about. But in this case, there's two places of uncertainty for the DER aggregator. One is in the real-time prices. You never know what that's going to happen with real time, and this is done day ahead, so you have to know how to bid into a day ahead flexibility market. And at the same time, you don't know how much your baseline energy consumption is going to be, and so that creates some uncertainty in how much flexibility you can offer. So that's essentially the objective. One of the primary constraints on the battery aggregator or on the DER aggregator is something we're calling a virtual battery model. There are a lot of similarities between DER aggregators and batteries. They have power constraints and energy constraints, but I'd say there's two main differences. One is, again, the baseline power. There's uncertainty. The battery knows exactly what is 0% state of charge and 100% state of charge, but the DER aggregator doesn't necessarily know where they are. The other thing is that your energy and power constraints can change over time. So imagine all of your occupants with smart thermostats come home and they all change their thermostat setting at the same time. All of a sudden, your 100% state of charge may become 120% or 50% of what you thought it would be. So a few results here. We used a co-simulation using some tools from NREL. We created, using data from NREL's Bienstock tool to generate a representative set of buildings, and then added smart thermostats and flexible capabilities to those buildings. Used the Ochre tool to do the simulation. We were looking at a hot summer day in Texas, so trying to flex air conditioning loads, and just trying to see how much flexibility we could get from these loads, flexing up and down. You can see the blue line is the actual amount of power consumed by the DER fleet. The green line is what the desired amount was. And so at certain times of day, especially for flex up, which looks like flex down, but when you're talking about DERs and consumption, everything is reversed. So flex up, there's no more flexibility available. People constrained their temperature set points, or essentially the DER aggregator wasn't able to provide the flexibility that it thought it could. I should mention for this the simulation, we made the assumption that the aggregator only has a certain amount of flexibility, wasn't able to change people's thermostat set points. They were only allowed to change the temperature within those set points. So a relatively small band, 1-2 degrees for most customers. And so we see here that they weren't able to flex more than about 20% of their baseline power. But if you had a program where you were incentivizing customers to change their thermostat settings more, you could potentially get more flexibility out of those houses. So another thing that we did for this project, we did some stakeholder interviews with DER aggregators to see what their needs were in terms of talking about and quantifying flexibility and uncertainty. And one of the things they came out with was they needed a simple way to talk to customers about flexibility and uncertainty of individual devices to convey essentially the value of the resource to the customer. Could be useful for customer outreach, figuring out which customers to enroll in your program, and also for determining incentives or compensation mechanisms for that program, potentially giving more of an incentive to certain customers that can provide more flexibility. And so the main thing was create this score, a semi-quantitative score that can give people some idea, kind of like a credit score of what the value of their flexibility is, accounting for the magnitude and the uncertainty of that flexibility. And the other thing to note here is you have to do it with very limited amount of data. So this is maybe when you're doing program enrollment, maybe all you have is AMI data, or maybe not even that, and a little bit of metadata about the customer or their house. And so we did some analysis on water heaters. We found that kind of the sweet spot of data metrics to look at was annual energy consumption of the device, the thermal capacity of the device. In this case, it's water heaters, really just the physical size, the number of gallons that can be held in the tank, and then the forecast error. How well can you predict the energy consumption today based on historical consumption patterns? So we've looked at these data, created these clusters, and the plan is to test these clusters out in the co-simulation framework and compare, see if there's ways to create scores where one cluster can perform better than the other in terms of the realization rate or the aggregator revenue. So just in summary, the main goals here are matching uncertainty with flexibility. Don't provide any more flexibility than you need to, but have a good handle on how much uncertainty you will have at certain times of day to determine how much your flexibility needs are. These flexibility options can be used, day-ahead markets, lower risks for multiple participants, lower system costs. And on the DER side, again, DER aggregators need to manage that uncertainty to understand how much flexibility they can actually provide. And these DER scores can be useful in communicating with customers. Thanks very much, and looking forward to your questions.